Good evening, everybody. We would like to begin our meetup as it's 7 p.m. and I hope that you're ready. We'll wait for a couple of minutes until everyone take their seats and begin our presentations. So, hello world. First of all, I would like to welcome you all who are here at Rocket Vilnius. It's a great pleasure to be here and welcome you all to the second official AI meetup of Artificial Intelligence Association of Lithuania. Also, I'm saying hello world to those who are watching us on the live stream. And so first of all, I need to say who are we, and we're proudly hosting this event again by Artificial Intelligence Association of Lithuania. In Lithuanian, our official title is Lietuvos dirbtinio intelekto asociacija. For those who are here for the very first time, those who are new, in these meetups, I would like to introduce our main features, who are we, and what defines the association. First of all, it's the most important to mention that it's a totally non-profit model. That means that all the membership fees, either individual or of the companies, are dedicated only for organizing the events and for the whole community. So president or other members are not receiving any remuneration, so it's totally free model. Secondly, our community comprises both AI professionals and enthusiasts. Like you will see during the presentations, we have two people who are working directly in the AI field. Personally, I call myself AI enthusiast as I'm a lawyer, but the thing that kind of fascinates me about the association that it welcomes members from all the spheres, and those who are interested are welcome to join and participate in our events. Third thing about us is that we are very aimed at knowledge sharing. We have a broad community of people who are willing to share their experience and knowledge both online and offline. I'm sure that during this meetup and all the other events of the association, you'll meet plenty of great, interesting, well-educated and people who have lots of practice in the field, and you can gain a lot of knowledge from them. And finally, we aim to have quality-oriented events. In the artificial intelligence group, previous year we had 12 events. This is our second meetup, but we hope that, of course, this is not the last, and we'll have many more in the future. And we have in plans conference in spring, so stay tuned and follow the news and social media and elsewhere. If someone's interested to join the association, we need to announce that we have a Google form, which you can simply fill in and join us just like that. We have membership fee, 100 euros per individuals and 1,000 euros for companies. It may seem a lot, but I'm sure that it's worth it as we have a growing community and we'll have more and more quality events, like I said. So for knowledge sharing and for our own good, I'm sure that it's worth it. How can we connect? So we have a Slack channel and a Facebook group. How many members do we have from these channels here? Can you please raise your hands? Well, about a half, I would say. So those who are not here yet, I encourage you to join us and participate in very interesting discussions. This is our main contact person. I'm saying hi to Audrus, who is currently in the New York City. He's sending his best wishes to our Meetup members and the participants. He's currently the president of the association and CTO at Agile company. This is the contact email address, president@lithuania.ai. You can email him and say your comments and your ideas about how you're willing to join the association and how to participate in the activities of it. I'm here, I'm Aurelija Šerniūtė. I call myself, like I said, AI enthusiast. I'm one of the co-organizers of this meetup, but my main occupation is being a PhD researcher at Vilnius University Law Faculty. I'm investigating modern technologies and their connection with human rights. The third person is Deividas Matačiūnas, who registered you all. Hi, Deividas. He's also a co-organizer of this meetup and data scientist at IBM. So yeah, you can either during the break or after the event, you can chat us up, ask questions, or anything else that's on your mind. We are the contact people who can answer you all that. And now, after all those introductory talks, which I hope weren't too boring, I would like to present our first speaker, Simonas Bastys, who is a leader developer at Pixelmator team company. As I know, this is their first and very interesting presentation about 6 projects that they've implemented during the past couple of years. So I give the word to you, and the floor is yours.
Thanks. Hi. So I'm leading the product development at Pixelmator team, and our product is image editing application for Mac, iPhone, and iPad. So we're working on Apple platform, and here I will try to speak about our development and research process, how we go to production with machine learning based image editing solutions. Since 2017, we worked over on 6 projects, and in this talk, I will try to briefly discuss about challenges we faced with those projects and interesting facts about that. So I will start with machine learning layer naming. So machine learning could recognize in your pictures objects, and we thought this is a very good use case for the tool where user adds image into his composition, and we could name it for him. So when user works on composition, he collects a lot of images or resources to his composition, and all of them have just random names, symbols, and that's it. And we would like to just simply name them the content which is in the images. And we thought this is perfect task for machine learning. So it's classification problem, and it should be easy. We hope that this project will be simple to do at first for us. But there is some key challenges. First one is that we hoped at least that we could use some public data sets. And there is a lot of public data sets. But the thing is that even the most popular and the big ones, like Coca stuff or similar ones, contain a lot of issues with them. So A lot of scientists are working on those data sets, but you try to use them for real-life photos, and you will see some bizarre examples. For example, they could recognize giraffe in your images because they have few thousand examples of giraffes, but they are not able to recognize the tree because there are 0 examples of trees. And we are not able to use them because just of simple fact that they're just not made for real-life use cases. So we had to build ourselves our data set of just how we would classify objects. The second one is our products are, it's something that we run on user devices, and when you download our application, it's you download with the application the machine learning model. So it means that when we distribute our application, we have to consider the machine learning model size. And you could get very good results with the ResNet 50 model, but it's 100 megabytes. And whereas our application is 100 megabytes also. So just adding this very small feature to be able to classify objects within your image makes your application twice as large. This is too big. If you will try to use some smaller one, SqueezeNet model, just 5 megabytes, but it's something you will not be able to use for production. It's just too imprecise. It gets you random classification, and you will try to drag and drop some images, and it will give you some random examples. We chose something in between. 30 megabytes, a bit too much for this task, but it was something good for us. It was optimal balance between size and precision. And we thought that we kind of got very good product, and the very last minute we got feature requests for us, and we are able to classify trees, animals, and stuff, very normal stuff. But we are working on Apple products, and for us it's very important to be able to classify, is it PC, is it Mac, is it iPhone, is it Android phone, and we thought we are not allowed to ship our product which will name every computer as PC. So in the very last minute we had to add Apple products to classify them. And we found out that even if we will add just few classes to additionally classify to machine learning model, it could just create disastrous results in other classes. So we added few classes, and that created imbalance within machine learning model. But for our business, it was very important. And it was very last minute feature request, and we had to add it, and we shipped the product which had Apple products, but didn't have very good precision. So that was business decision, and it was kind of disappointing, but we shipped it. And we hope this product could be shipped in a couple of weeks, maybe a month, but it actually took 3 months of dedicated team working on just simple problem of classifying objects. And when we started this project, we hope this is something actually done, and it shouldn't be a problem, but to make it to production, to actual product, it takes time. So it was surprising, but yeah, the product was nice. I will show you a short marketing video we made for this feature.
Machine learning is a technology that allows computers to learn and then use that knowledge to perform tasks more like a person than a computer. One incredibly cool and handy way that Pixelmator Pro uses machine learning is automatic layer naming. Simply take any image, drop it into the app, and whoosh, just like that, Pixelmator Pro automatically recognizes the contents of the image and gives your new layer a name. And not just any name, but one that tells you exactly what's in the image. You can drop in images from pretty much anywhere on your Mac, like your desktop, the Photos app, or any other app. If you want to see a few more name suggestions, just control-click the layer in the Layers view and go down to Suggested Names. You can even drop in a bunch of different images at once. And one by one, they'll be named for you.
Yeah. So next project we took was, we thought that machine learning could understand the object. So it should, in theory, understand that the object has its own bounds, and we could select this object. And in image editing, it's very important to be able to select object, because when you can select object, you can change colors, you can add effects, you can remove object, or you can add object to another image. So this is very important for image editing, and we thought that machine learning could really help us here. And we defined this task as class-agnostic and instance-aware image segmentation. So class-agnostic means that we would like to select any object on the image, even if machine learning haven't seen it before. And instance-aware means if there is object overlapping each other of the same class, two apples are overlapping, we would like to select them separately. This is something we would like to have in our application, and it sounded cool, and it's actually very hard to do and almost impossible in traditional computer vision. And we thought machine learning could be an excellent choice here. So there are some key challenges. The first one, we learned that state-of-the-art research is able to work only on fixed classes. So the best science we got is just working on the classes which machine learning model was trained on. So for example, it could recognize only machines, people, and animals, and that's it. If you have tree, it will not be able to classify it because it haven't seen it. So that was very limiting for us, and we thought, okay, that's something we could try to tackle ourselves and try to fix that. Instance-aware segmentation also was something not present in research, and we thought, again, it's very important for us for the product, and machine learning should be able to do that. Third one, in 2017, when we worked on this project, no state-of-the-art research was done with requirements we had for our product. And we felt that we are on our own to do something new in this field. And we are just recently learning that this year, with such requirements project, is able to reach only 20 median average precision, whereas 70 or 80 needed for production. And ultimately, we spent 6 months of team work on this product. We hope to invent new stuff here, but simply we spent 6 months of team effort on this project, which was impossible back then, impossible today, and maybe this is something for the future. I hope to revisit it later on. Next one, machine learning enhance. So there is a common problem if you have some picture and it has, for example, in this one, it has blue offset, and we like to fix it. And if you would see this image separately, it's hard for human eyes to fix it, and you probably need at least a couple sliders for that. And we hope that machine learning could recognize the content of image and could know the original colors that was for the object, for the skin color, and could fix that for us. So we defined this problem as content-aware white balance tone and contrast correction tool. And there were some challenges. The first one, you have to create dataset with millions of examples. And you have to have bad and good image. So you will train a machine learning model to make bad image look good. And here's our strategy. We thought that we are not able to do that manually, and it's something we should try to do automatically. And our strategy was, first, let's gather just any image we have from internet. And we got tens of millions of images, and we had just few terabytes of random data. Second, we handpicked only 30,000 images we thought in our view are representing good images, and with good white balance, good tone, and good contrast, and just good pleasant colors. And from those images, we trained a data analysis model which could understand what we consider a good image. And then we removed bad images from those collected images in the first step. 30% images remained that we considered as good enough for our training. Last step was we have few millions of good images, and we have to somehow create bad image pairs. It sounds simple. You will just simply try to change some, to add some random permutations in your image, change RGB values of your image, just destroy image. But what we found that if you will try to destroy it simply, like you would do that in image editing app, you just move some sliders of red, green, blue channel, machine learning model will learn that, fit over this approach, and will simply able to fix just synthetically destroyed images. So it was very long process just trying to find the approach that a machine learning model will not understand. And the best way we got is we had to destroy images not in RGB color space, but in perceptual color space. So LAB space we used for destroying images, and that worked. The last thing, when we got pretty nice results and we worked on this excellent data set, we had problem that machine learning model operates only on small images. So when you work on machine learning model, your input is very small image, 100 by a few hundreds by a few hundred pixels of size. And your actual image, which you would like to fix, is few thousands by few thousands, so 10 times difference. How you do that? How you will transfer your machine learning model output to your final image? So first approach is you have your bad image, you make it smaller for machine learning model. And for machine learning model, you ask to output slider values for your image editing application, and that will fix your image. But this approach is not very flexible, because when you train your machine learning model will have to learn about your application. It will have to learn how your sliders work, how you implemented your fixing sliders to fix colors. And if you will add some more features or you will change implementation, you have to retrain it. So this is very limiting, but this we would call end-to-end machine learning, but for production we thought this is something not for us. And we created different architecture for that. So instead of asking machine learning model to provide slider values, we ask it provide very small image, the same size it got as an input. And then we use the input image, we add to the output image of machine learning model. We do some other machine learning task here, just to try to compute the best values of our sliders, and only then we output the final image. That was very good for our product. We are able to introduce new products based on this approach. We are able to change our implementation of our tool, and it just worked. So with this single machine learning model, we could do a lot of very cool stuff. And I have a very short marketing video.
Thanks to the Core ML-powered ML Enhanced feature in Pixelmator Pro, making your photos look stunning couldn't be easier. How? Well, here's a photo that could use a little work. It's overexposed, and the white balance isn't quite right. You could open up the color adjustments and take care of all of this, going through individual adjustments like temperature, tint, exposure, shadows, highlights, and others. But with Pixelmator Pro, there's a much easier way. Just click ML Enhance, and Pixelmator Pro does all the work for you. Using an innovative machine learning algorithm trained on millions of professional photos, Pixelmator Pro instantly makes adjustments to the white balance, exposure, and even individual color ranges in a photo. In fact, ML Enhance fine-tunes 37 different adjustments. So, to make your photos look stunning, all you need to do is give them your own creative finishing touches. And just like that, you've turned a good photo spectacular. With ML Enhance and Pixelmator Pro, bringing out the best in your photos is unbelievably quick and incredibly easy.
Next one, machine learning crop. We had this idea, when you have fixed colors, maybe you would like to fix your composition. So our task was very simple. Let's try to crop image for the user, keeping his main subject, but just offering different view for this image. So from portrait, we could have just square image, and it just looks different, and for some users, it would be preferred format. So our task for machine learning model is just propose alternative cropped compositions for the image. And the first challenge we got in this area, in previous areas we worked on, there was some active research, and we could borrow some knowledge. But in this area, we looked and we found nothing, and we felt like we are trying really interesting things no one was doing before, and that was at the same time challenge. It was fun also. We tried one thing from previous project. We tried to just gather some good images, and we tried to teach machine learning model only on good images without any guidance how good crop would look like. That failed. It was not possible to train machine learning just simply showing good images, and you have to provide some guidance. How would you like to crop them? And we thought that we had, again, very good product, and we tried to integrate that into our application. We started user testing, and we got one feature request. User would like to crop his image on his defined aspect ratio. Our first goal was just simply we will try to offer any aspect ratio machine learning model could dream of, and it would be single one. Feature request from the user is user would like to define if he would like to have portrait photo, landscape photo, or just square. And that meant that our work is just not working. So first approach, proposed single rectangle is not working, and it's what we created is not something user wants. And we had to work on different architecture, which we don't ask machine learning model to simply output single crop rectangle. We ask it to provide the heat map of possible cropping rectangles into image. And only as a second step, we, based on user aspect ratio requirements, we propose cropping rectangles. And that meant that first solution took a couple months to develop and deliver. We had to drop it and to work twice as more just to deliver fixed solution. We were not able to reuse or simply fix or add this feature. This is something was surprising for us. Seemed like simple feature request from the user standpoint, but it meant that from the business perspective, you have to start from scratch. And we finished this project, and we launched the Pixelmator photo image editing application for the iPad. And this was a successful launch this year, and a couple months later, we got Apple Design Award. And for Apple Design Award is not about only design, It's about technologies also. So this product got Design Award for its use of machine learning. And I think we are still in production. Our product is still alone with machine learning use for image editing tasks and on Apple platforms. There are some companies doing that, but not as wide and as hyped as you would think. This is something very new, and just this year we launched this product with machine learning tools, and this is still considered as very fresh and new thing. Next project we worked on was machine learning the noise, and again, you probably seen that with your images. You have grainy image from your camera and you would like to fix that. If you will use traditional applications, when you are trying to fix your photo, you will make it simply blurry. It will not look better. It will be blurred out. And we thought that machine learning could fix that. Machine learning could understand the content of your image and could try to recover details which are obscured by noise. And yeah, this project was very challenging. Even though the definition of project was very simple, just try to remove camera noise. That's it. Some key challenges here. We would like to do nothing for your image if it has no noise. Any image noise removal tool you will have on market today, it will try to do something. Even if it's not able to do anything, it will try to blur your image, to destroy. It's not intelligent at all. We would like to be intelligent here, and we will try not to destroy your image in case we don't understand your image content or image noise. Of course, there was no public datasets for this problem, and we had to build it our own. And it's a very popular topic in computers, in machine learning science, but with camera noise, we haven't found any good quality datasets. And before starting to remove noise, we learned that we have to build one more machine learning model. We have to do analysis of your noise within your image. Every image has different levels of noises, so every image contains fingerprint of your noise, so it could be small, medium, and large, and they could have different values for each image. And before starting to do noise removal, you have to do analysis. Next one was the most challenging. So this project was with the idea that user will see the machine learning model output with his own eyes. So we will pass image at full resolution to the machine learning model, and we will expect it fixed output. Machine learning model has many layers. And when you are passing image with those many layers, your image could be destroyed. Machine learning could introduce some artifacts, coloring issues, or random details. So first thing we had to do, without any noise removal, we had to make machine learning model just to take input of your original image and to output the same image. It was the most challenging task in this project. Do nothing. It was very hard. And we worked on this project for 1 year, and users said that it's not good enough. We launched it a couple months ago, and users just said, no, it's not working. And we tried to investigate why users think that. We thought that we achieved something that's never been achieved in science, but users were looking for different stuff. Users were trying to fix not camera noise, but synthetic noise. So users sometimes just expect that our tool, because it's machine learning, could fix any type of noise. And that's very different. We built this tool with the idea that we will fix camera noise. And we are not building tool to fix synthetic noise, which was added with different application. So this is the most challenging project we had. The users were like, felt that it's not good enough. And what we are working to fix and to add synthetic noise removal. It's not as challenging as camera noise removal, but still we are working on that. One more project, machine learning-based super resolution project. We thought this one will be easy task. And the idea is just user has very small image and user would like to make it bigger. And this is image upscaling while resynthesizing details and textures within your image. So this problem in machine learning community is very popular and very exciting, and we've seen a lot of research in this area. But we learned that it's not something ready for public use. So there was some key challenges while working on this tool production. The first one is almost every image on internet has, for example, image compression or JPEG artifacts. And if you will try to use any state-of-the-art research on images with your JPEG artifacts, you will see that instead of upscaling image and making it nice, state-of-the-art research will simply upscale those artifacts and it will look horrible. So our idea while building this product was just, let's try to fix that. Let's try to think with that our users will try to use this tool on images with compression. So the next one, image noise handling. If you will try to, again, upscale your image with the noise, you will get very strange looking result. The noise will create some texture within your image and it will look bad. This is something we had to build into our tool and to make it look better. And our approach was, instead of trying to consider noise as a part of image, we had to separate it from image. So we separated noise from the image and scaled separately. And that created excellent results. And again, this is something never done before in our view, but this is the way to go with image noise. Image transparency support, state-of-the-art research, again, ignores the fact that your image could have some transparency. And all research is just ignoring this alpha channel or transparency in your image. But for our users, I easily imagine that you would like to, you have some logo with transparency within, and you would like to make it bigger. So this is something, again, we had to build and to fix with our own research. And the last one is that in this area of research, researchers are not thinking about memory consumption or processing power. They're just building huge solutions and they are not considering user devices. For us, it was the most challenging part of this project was that state-of-the-art research is not applicable for user devices. If you would like to run this project on user device, you could simply ignore last 3 or 4 years of research because it's not applicable for the user device. It's applicable just only for very powerful machines. So we had to invent and work on interesting approaches just simply to be fast. This is very important for production. We'll launch this tool later this month. I am the most excited about this tool. It's really cool and it looks good. I don't have marketing video yet for it, but it will be really amazing. I have very short summary. So it's theory that data sets are very important for machine learning, but in our experience is simply the key for any machine learning project. And we thought that we will have shortcut with public data sets. it's not good shortcut. You have to build your own data sets anyway. So in our company, we are working for 3 years on machine learning, and more than half of our time is working on data sets, improving data sets, collecting data sets, fixing bugs in data sets, or just manually trying to find ways where it's broken or where is bad data appears. It's very large part of work with machine learning, and it's very important. The creating machine learning model or those architectures of machine learning is very cool and exciting, but the most important part is data sets. Second one is that state-of-the-art research is most likely not something ready for production, even though you will read papers and it will look like it should work. It doesn't work in practice. It looks good on few example images and that's it. Don't be excited about that. You could borrow some ideas and to learn something, but it's not. You could not build product out of state-of-the-art machine learning. We are coming from the, I would say, classical computing field. Our company is 12 years old, and 3 years ago we started to work on machine learning products. And we know how hard it is to predict classical computing IT projects. Computer vision projects it's quite hard to predict. But machine learning projects are a different level. It's hard to predict if they will succeed or fail. So from business perspective, it's something you should consider that you have to have not budget for one machine learning project, but you have to have budget for 2 or 3 machine learning projects if you would like to ship some product with machine learning solution. So instead of building just for one solution, you have to consider that you might need to build the same solution just with different requirements as we had for example, machine learning crop, and to invest much more than originally planned. And the last one is, in our view, machine learning works best to improve something existing. We don't see that product could be built just purely out of machine learning. We've seen a lot of companies who tried to create machine learning-based image editing and used only machine learning. All of them failed. And in our company, machine learning is just part of product. We are using machine learning just to fix some pain points in user workflow, or to improve experience, or to add some additional workflows. But we are not building machine learning based complete solution. We are building just to improve existing solution. This is it. I would like to say that if you would like to get access of our tools, please write email. I'm happy to provide you free access to Pixelmator team machine learning products. This is it. Thank you.
Thank you, Simonas, for a very interesting and systematic talk. Now I would like to give some room for questions. Does anybody maybe have already of them? Yes, please.
How did you handpick 30,000 good images?
By hand. We're just simply looking at that. We had so few millions of images, and we scroll them and picking, this is good, this is good, this is bad. Yeah, we've built very simple web-based tool, but the fun story is that while we try to pick 30,000 images, we change our requirements. What does it mean, good image? So, and actually we changed those requirements a few times. So actually we handpicked over 100,000 images, but only the last 30,000 we considered with good requirements for the good image. When you pick 10,000 images, you try to understand, you're starting to understand what does underlie good image. So it took some trial and error method just to pick those 30,000 images.
Do you use any kind of, voting? So 3 people are saying this is good image, bad image.
We,
The same image, I mean, like if 2 people say good, the first one says bad, it's good.
we try to, for consistency, we used only very few experts here. So we haven't used mean observer score or something just to make rank them, but we just simply consider that this person, we trust him, he will pick. That's it. And this was very important, and and I don't believe that if he would assign like some random people, we would have some average values, average decisions, and we picked the expert, and we actually, was one person.
Do you need a microphone?
How often do you update your models? For example, this one, do you update it often? Do you include new images?
Yeah.
Or it's just one time
Yeah, okay.
and you use it for...
I will repeat the question.
Thank you.
So the question is about how often we update our models. In practice, we ship products every few weeks, and we ship updates to products every few weeks. Machine learning projects are taking a half or 1 year to develop and to make to production. We haven't had any time to update any of these models. We worked for quite a long time. We have all pipeline to update them, but we reached the quality requirements we made, and we shipped the product, and then we started to work on the next one. The exception is machine learning-based denoise, which, because of user requirements, we are adding one more additional feature to denoise synthetic noise. And this is, I think, will be first time when we will update the machine learning model.
Some models are good because they update it frequently. Because
Yeah.
it's some new information. And so I would thought that it would be very difficult to update this model frequently because you need to collect images and as you said, it's the...
Yeah, it's for us to simply, we are looking into, we are collecting data for machine learning enhanced color project. We are collecting data, but for us to make it really worth it to update, we have to work for a few months to make a really noticeable improvement here in this area. If you will simply add some more examples, it will fix some examples, it will destroy some other examples, so it will create imbalance. And this is something we learned with the first project. It's not very good, and we are trying to avoid that, and we are working on a long term.
Yeah. When you started testing your model, did you receive any totally unexpected output? And if yes, what was it?
Yeah, we got a lot of that. So we start to test our products early on, and we build prototypes, and we start to see how that works. And for one example, machine learning enhance project, we started test after 1 month, and we worked for full solution for 1 year, so 11 months of testing. And every couple days we had new machine learning models, and we ranked them. We tried to understand what kind of diseases that they have. We called, when model has some issues with recognizing and understanding or fixing issues, we call them diseases. So it would not recognize some kind of objects, it will fail on other scenarios. And just, it's a lot of, we've seen every possible issue with our models, every possible. So it's iterative development with that.
A little bit on the testing. Did you build any automated or semi-automated testing rigs to basically to repeat your Because you develop new models quite often, right? On kind of
Yeah.
while developing it, how do you make sure that it does, like, you fix the disease and then it doesn't appear later? And how to reduce the, like, a manual labor that you have to go and check all of them, right?
Yeah, so we have, of course, automated testing, but this is, again, it's very hard with machine learning models. Sometimes you will get with automated testing, oh, that's fine, it's good, the numbers are looking good. We are working at least on several metrics for each model to see if it's not if it does not expose some interesting issues. But at the end, for verification part, we assign ourselves to test it. The human eye is the last deciding factor. Is it going to go to production or not?
Can you maybe approximately say how much effort, like human labor, you had to spend on this, specifically on testing?
Okay, I have no idea. Months. Yeah, it's very long process.
So thanks for presentation. My question is about data. Are you able to collect data from your users, like the noisy picture from users, and when we correct and train on that, or no?
We are not collecting any data implicitly from our users. So if users will send image to our support channels, we will try to use that image, at least in the verification part. But it's something we are not collecting, and we have no idea how our users are using our machine learning tools. It's something we are just getting in feedback form. They like it or hate it, and that's it. Sometimes they share examples which are not working with us, or sometimes they do share success stories in internet. Look how good the tool is. But that's about it.
So first of all, thank you for a very comprehensive talk on the subject. You really have excellent promo videos. I enjoyed watching those. In all due seriousness, so you ship the models with the app.
Yeah.
That's why you're concerned with the size of the models.
Yeah.
Have you considered keeping the models like on your side in the cloud somewhere, and you let the app use that as a service? You'd be able to update them constantly, or if not, what's the limiting factor here really? Like the connection speed or what?
Yeah, so for us our application is image editing application, and we consider for image editing you don't need to have internet connection. So I think this is something how we imagine image editing. You don't need to upload your image and to get some data from internet. And we would like to use such program which does not just uploads your images. That's one thing, but the other thing is the performance. For us, again, it's very important performance, and we aim all the time for real-time performance. Machine learning is hard, but this is something we are working very hard, and we are working on performance of our machine learning models. Even on device, it's challenging to achieve that, but on the server side, if you would do full-size image inference, full-size image fixing, I have no idea how long it would take. So this is something we haven't even considered because of those constraints. Yeah, if that answers the question.
Yeah, definitely. Thank you.
So thank you all for the questions, and of course, thank you very much to Simonas for the great talk. And now we have some good news for you. During the break, you're all welcome to enjoy the snacks, pizzas, and drinks sponsored by Pixelmator team. And we'll be waiting for you at 8:10 for the second talk. So see you later.
Hello. So we start in a few minutes. Yes.
Čia tai šviečia. Pabandykit čia. Ne, tai man reikėtų. Ne, šitas tiesiog per silpnas. Supratai? Bus pirštuk.
Staigiai greitai būtų ir po to sulėtėja biškį. Tada userio tas laukimas biškį atrodo ne taip lėtai skaičiuoja procesą. O mes šitą naudojam ar CNN modelį, 100 megabaitų. Sistemoje daugelį modelių turi, nes tiek serveriai naudojam pas save.
Žinau, nes daužas sakytų čia.
Kiek metų dabar sąskaitas atlieka segmentavimą. Tai kai tu tais toksai įsigūtų tokių 5 megabaitai ramų.
Nu, nežinau, nebent jeigu galėtum čia prasidės. Dėžės reikia nešti už tenai ir už pastą. Jo, yra suklaidai. Ir bent jau vieną vietą kažkokią sudėjo.
Matęs toks dalykas.
Kad tiesiog
Žodžiuoju dabar darom su
ir dar nežinau, ką daryti su ta dėžė ir dar liks ir kažką sugalvoti.
Keliausiu.
Pradedam?
susijęs irgi tema, nes mes darom webinių vaizdų elementų aptikimą. Batom, jūčiai.
Atsiprašau, biškį, galėsi tu padėti perimti, gerai? Tas skaidrės. Tai aš pristatysiu tada ir gerai? Jo, ten kaip ten tu per tuos ekranus pravažiavai. Jo, tai gali dabar iš tikrųjų. Dabar gali perimti. Skaidrės kaip ten.
So we are starting right now. So thank you Pixelmator team for food and snacks and amazing pizzas. And we have a second guest speaker, which is Donatas Repečka, deep learning scientist and co-founder of Biometer Design. And today Donatas talk about engineering synthetic proteins using generative adversarial networks, or GANs. So please welcome Donatas.
Thank you. Okay, I'll give a minute or two. So I guess I'll start slowly and then people will join. So good evening. My name is Donatas and I'm here today representing a young startup called Biometer Designs. We are working at the intersection of artificial intelligence and synthetic biology. And today I'm gonna talk about engineering synthetic proteins using generative adversarial networks. And if you like me, when someone says proteins, you think about the food proteins, the ones you need to put in your diet to build muscles. However, for this presentation, I'll ask you to adopt a new definition of proteins, which would be programmable nanorobots performing specific function. And it's used widely by nature. pretty much every process which is happening inside us is driven by proteins. And on your right, you see a visualization of one protein in the cell performing a transportation. So it's moving things around. So I hope that helps you to get a better understanding about what kind of proteins I'm going to talk about. Well, it's animated, so no, but the actual principle, the way it works, is actually quite accurate. It has legs, not that nicely defined, but yeah. Okay, so just to add on proteins, and then there is another word, enzymes, which is just a subset of proteins, so they both pretty much mean the same in the context of this presentation. Right. So once we get that out of the way, let's talk about quite big issues which we face nowadays. So we have CO2 pollution, we have clean water problems, and we have quite a bit of plastic which we can't recycle easily. And that happens because we move so fast. Our technology is advancing so fast, and nature can't cope with that. It's a bit too slow for us right now. But it's a question, can we use the things nature creates to help us to solve our global challenges? And in fact, we start doing that. We do have some enzymes which are used in water filtration. We have enzymes which help to reduce carbon dioxide emission. We even found recently an enzyme which can eat plastic. So that means converting something smaller, which is less harmful. However, at this point in time, we don't really understand how the protein works and why they works. And it's quite key point here that we found it accidentally because we don't understand the principles. And let's see why. And the reason is because it's a bit tricky. On the screen, you see two proteins. Actually, one of them is working, another doesn't. I could ask which one, but nobody in the world can say which one just from that. So it's tricky. So this is the protein. Every letter is an amino acid. Nature used 20 different amino acids to construct all the proteins we need to survive and do all the kind of stuff. And this sequence of the amino acids determines the protein structure and its function. And on your right, there is a 3D structure of the protein, and just to get the grasp of the complexity we're dealing with. And let's put this into perspective. So we have a faster computer which can perform that many float point operations per second. We have the age of the universe, and we have the number of the atoms in the universe. So let's plug the numbers. We take the fastest computer. Let's convert each atom to be the fastest computer, and let's run it from the beginning of the universe. And we get 10 to the power of 115 operations happen since the Big Bang. Then we take the average length protein, and we can have that many different combinations. So brute forcing isn't an option here. So what do we do? And well, people are quite clever, and they find the way around it. Nature can change the proteins, so we can take what nature does and speed up. And the current method, the state-of-the-art current method, is a directed evolution. And the principle, the working principle is as such. We take an original input, so original sequence, we do random mutations, we select the best mutants, and we repeat the process. And that's how we get new proteins nowadays with different or improved functionality. And it's actually quite good, and it's appreciated. In 2018, Nobel Prize Committee awarded Arnold Francis for pioneering idea of directed evolution. And if you read the press release there, you will see how widely it's used and how many problems it helped to solve. However, from looking at this approach, it seems a bit, still a bit brute force. It looks like we can do better, and there is a question, can we do better? And we asked ourselves this question at the beginning, and then we looked at the artificial intelligence for inspiration, and we found the idea of generative adversarial networks. And if you don't know, these two, they're kind of famous, but these two people don't exist. They completely generated by computer from the random input. So let's dive into what generative adversarial network is. So generative adversarial network, or GANs for short, consists of two networks. One is called generator, and if you look at it's simply looking model. So you have the model, which is a deep neural network. It has to have loss function. It has an input and an output. The only difference from the very standard classification models is that you produce an image as an output. But from technical point of view, that means just you need more numbers to get out of the network, since pixel still is a number. However, the main problem here is how do you tell if the picture you generated is good, so you can optimize your neural network, train your neural network. And that's not trivial at all. There are no good mathematical rules to do so. So what do we do when we don't know how to solve the problem? Well, we use another neural network to do that for us. So we create another model. We would call it a discriminator. That's also a deep neural network. This model's task is to say how good the picture looks. And it could be probability or a number. And we feed that back to first model, and we can train it, because now we measure how good the picture looks like. Now we have to finish the second model, so we need to input to train it. So we take an input, and this is quite simple. So we need a classification model. So we need the real images, and then we feed real images and generated ones, and we train as a classifier. Now, important thing to note here is that, well, first, let's simplify. We just rename it. We have generator and discriminator. So important thing to know that these two models, they have opposite goals. They're competing against each other, hence adversarial. Generator tries to fool the discriminator, providing realistic-looking images that discriminator can't distinguish. Whereas discriminator goal is to distinguish well, to have a low loss. Another quite key point here is that generator, which generates an image, never has an access to real examples at all. So it can't copy, it can't take parts from one image and combine with another image. It actually gets an input random number, which doesn't mean anything, just a starting point, a different starting point every time. Sounds good? And how well does it work? Well, it works quite well. This is me generated by an implementation of the GAN called StyleGAN by NVIDIA. And with the right input, you pretty much can find any person there. And Yeah, that's generated completely from random noise. And with this idea, we thought, can we apply this to proteins? So we developed what we call protein GAN. And as you can see, we have same two networks, generator and discriminator. We have a random input, we have generated sequences and real sequences or natural sequences. And all looks good. However, there are quite a few challenges you need to address. So I put 1 out of 20 just to show that there are a lot of them, and I'm not covering all of them in this presentation. Otherwise, we'll stay until midnight. So this is just a short summary of that. So let's start from the beginning. The data is quite problematic. It's difficult to acquire. You can't take a camera and take a picture of protein and you have it. You actually have to do experimentally, and that costs. Also, when you look at those letters, you don't have a clue if it's good or bad. Is it actually, do you have to filter that, or any information about that? You can't do that easily. Data augmentation, whereas with pictures, you can do quite a few things. With sequences, we actually struggle to come up with any really good examples. Evaluation of the performance of the model as well. GANs are tricky on its own, combined with proteins. You can't tell if your generated sequence is good or bad easily. We turn to bioinformatics to help us out here. We got some metrics, they're not perfect, but they guided us through this process. And then the neural network architecture itself. Whatever is now out there, state of the art, and whatever I showed you before, it's pretty much all with images. And we are dealing with sequences, and they are discrete in nature. They have a requirement of capturing long distance relationships, because in sequence, it could be very far apart, but in 3D structure, you get those amino acids quite close to each other. So, complaining aside, 9 months later, we had a final version of Protein GAN, which grew into neural network architecture that contained 45 layers. It had 60 million parameters. And we trained that for 9 days using NVIDIA P100 with 60 gig of RAM. And finally, we got them. We actually ordered them physically, and it's quite fascinating. I haven't been working in a project where I actually physically can touch what I designed using computers. This time was different. So in that plate, there are some proteins which we generated using computers. And then there was a long period of experimental testing in the lab. With the help of Vilnius University and Chalmers University in Sweden, we got the results. And the results are as follows. 24 of generated proteins folded correctly and performed the function we wanted. Some of the generated sequences had more than 100 mutations compared with nearest neighbor in nature. To put that in perspective, to find a single sequence with similar diversity using random mutation, you would need to check hundreds of billions of sequences. It's not too bad if you think about the high throughput methods in synthetic biology. They can do millions or billions of sequences in one go, but that still takes some months to do, to design the experiment itself and to do all the things. It's slow. I talked about directed evolution. If you use that method to achieve the similar diversity, you would need 12 rounds, and each round taking from 2 to 4 weeks. So you can calculate how long that would take to get there. So what is the outcome of that? We have a tool now which allows us to generate diverse proteins, which can be used for searching for new properties. Could be more active, could be more stable. In a broader sense, we actually are the first ones to demonstrate the fully functional, fully AI-designed proteins. And we tested them in lab, they work. And finally, it's probably more for us, it just proves the deep learning ability to help with the problems which exist in synthetic biology. What next? We continue evaluating our technology. We just ordered 11,000 sequences, and we're gonna do lab experimental work on those. We're still trying to address some current limitations because deep learning models in general requires a lot of data. However, the most interesting applications doesn't contain a lot of data, so we're trying to solve that. These things aside, we're also exploring new ways how we can apply deep learning or artificial intelligence in synthetic biology. So that concludes my presentation. I just wanted to say that if you are interested and you have any ideas, please do contact us. We're happy to talk. We're happy to chat. And now, I'm just wanted to thank you, and I'm happy to answer any questions you might have.
Maybe we have some questions? Yeah, maybe we have some questions from the audience?
So, what applications are you most excited for the potential?
It's a good question because, like, once you learn, I suppose now, with what we developed, we're not quite sure how far we can go. With ability to design proteins, you name a problem, I probably give you a solution. So that's the power of it. Yeah, that's probably even could be possible, I guess. But yeah, I suppose. But that just shows the potential here. But I think for me, the most important thing is to solving the global problems. I'm super exciting about possibility to deal with actually mess we created as a human beings in the nature, all the pollution, all that. That would be amazing if we could just undo all that. And I think we'll focus on that.
How about the generation of DNA?
So,
for example, this like model like conditional can, the conditions phenotype, the properties of that picture of DNA.
Yeah, I guess that's in theory possible. Since we don't work with DNA directly, I don't know, I'm not sure how feasible. I saw the papers which tries to use generative adversarial networks to generate DNA as well. But I'm not really in position to say how well and what is possible with that. Yeah.
And I understand you are capable kind of producing sequences which work.
Mm-hmm.
And do you, so from what you're saying, are you capable of understanding what they will do?
Yeah.
How they will behave?
Yeah. So in this particular example, we chose a class of proteins which function we know already. So we know what to test for. Now, if we try to do something novel, a function we don't understand, so there is a problem with testing. What do you look for? And this is very interesting topic, and we are actually thinking about how we can apply this, but I don't have really concrete answers. How would you do that?
Can I clarify the evolutionary method you described?
Yep.
Why does it take each round? Why does it take 2 to 4 weeks? Growing step?
Yeah, well, again, I'm coming from computer science, so I might be wrong with details, but there is a period where you have to grow the bacteria, so that takes some time. So you put the proteins into bacteria, and then they grow, and then that's the way you test it. There is also a lot of work on preparing the right library of proteins. So you just select first, and there's a cloning and all that manual stuff which a human does it. And there are hundreds of ways how you get it wrong. So it doesn't really happen successfully every time. So that costs also time. So this is probably like very realistic time estimate, including all the hiccups you meet underway. Yep.
Okay, for example, if you're gonna break the rules and you're gonna go further to growing blueberries underwater, would be sounds possible or no?
Say again?
Growing blueberries under the water?
Yeah, I think so. It's the fact that you have to, so like what you need oxygen now to grow and like CO2. So you just need to change the mechanism. So you can produce the sugar from wherever other elements as well. So it's just a matter of finding the right chemical reaction to provide the components you need to grow the thing. So if you have that chemical reaction, then you can build, in theory, that's not possible at the moment, but in theory, you can build a protein which does that, and then everything else is possible. So in theory, yes. Practically, probably, I would say at least 20 years from now.
So if you don't have any more questions, so thank you, Donatas, for amazing talk, and thank you, our host, Rocket Vilnius, and we see you next time, next year. Yeah.